All right, so let's take a look what's going to be on your Unit 3 exam, just kind of some hints. The first chapter, Chapter 7, we talked about the terrestrial planets, the 4 inner rocky planets, and of course we talked about planetary differentiation, and that is kind of akin to salad dressing, where basically, Italian salad dressing, I guess should say, where the water sinks and the oil rises, because the water is more dense and the oil rises, is less dense. So planetary differentiation, the dense heavy metals sank to the core and the lighter materials rose. Now, one thing I added is that actually this can only happen if you have it's still what I say, ooey gooey, it still has a liquid interior. Magnetic field, actually we can create a magnetic field if we just have charges that are moving. And so planets create magnetic fields only if they have some liquid in their interiors and they're still a little bit ooey gooey, and they have to have a significant degree of rotation, because it's that planet rotating on its axis that actually spins those charges that creates the magnetic field. The next term actually goes along with that. We call Earth's magnetic field, we call its magnetosphere. And actually, then when we talked about in the next chapter the Jovian planets, actually Jupiter has a crazy, humongous magnetosphere as well. But magnetosphere is basically the magnetic field that surrounds the planet. And the Earth in particular is protected by our magnetosphere from harmful charged particles coming from the sun. Greenhouse effect. So I brought in a figure from your textbook, and I know it's kind of small, but this table 7.1 actually lists Venus, Earth, and Mars with regard to what their temperatures would have been without the greenhouse effect. And Venus has a crazy greenhouse effect. I mean, it just means it has specifically, again, carbon dioxide in its atmosphere that traps otherwise outgoing heat. Mars doesn't have much of an atmosphere, so remember on this table 7.1 it didn't have much of a greenhouse effect. And the Earth has kind of a moderate amount of greenhouse effect, and it's kind of like, reminds me of like the 3 little bears, where, you know, the baby bear gets just right, right? So anyway, the greenhouse effect, I like this figure from your textbook that has kind of the yellow over here on the right. The yellow rays is the energy from the sun that's coming and striking the Earth, and it comes through the Earth's atmosphere. That sort of visible radiation comes through the Earth's atmosphere. Some of that visible radiation is then transferred into thermal energy, and so the thermal energy would be the little red sort of squiggles, and so thermal energy is blocked by those greenhouse gases. So that's kind of how that works, and actually it's a homework question too. The next one simply is the fact that on Mars we actually have two surface features on Mars that you need to know. One is Olympus Mons, which is it's like an extinct volcano, but it's more what they call a caldera. It's kind of like, it's just humongous. There's not much of a cone, really. It's kind of a flattened plateau caldera. But that's Olympus Mons on Mars. And then the other thing on Mars is the thing that's kind of like the Grand Canyon on steroids, called the Valles Marineris. It kind of goes along Mars' equator. So we know those two features. The fact that Mars has this red appearance, that's because the iron on the planet, planet's surface anyway, actually combined with oxygen early on to form iron oxide. It's rust. That's why Mars is red, because of its kind of rust in its soil. Martian atmosphere, why did it change? And I went ahead and brought in this figure from your textbook. Basically, it cooled because it was smaller than the Earth. If we compare Mars to the Earth, it's only like 10% of Earth's mass. So it cooled, and then it lost its fluid on the inside. It became solidified, so actually, as it rotated, it could not create a magnetic field. So this is kind of showing you from left to right. It used to have a magnetic field, and then it cooled and does not have a magnetic field. And the consequence of that, we talked about, is then that the sun's charged particles, or the solar wind from the sun basically can blow away the Martian atmosphere. Downstream, that's where the Martian atmosphere went. The next one, reshaping of reshaping of the surface of the terrestrial planets. We have cratering, volcanism, tectonics, and erosion. Remember, erosion could be either wind erosion or water erosion, but those are all ways in which the terrestrial planets get their surfaces reshaped. We talked about two features of the moon, the mare and the highlands. And so actually the mare, I brought in a slide, a figure here to show you how those mare formed. Remember, the mare are the dark colored regions that we see from Earth, and they are kind of flat and smooth, and this is kind of why they're smooth. That kind of from left to right, here's a cool figure from your textbook. It shows you that, go back. Okay, it shows you that Mars, early on, it did have liquid in its interior, and so basically with the bombardment and such, it got bombarded to the point where some of those regions, those crater regions, were thinned out such that the lithosphere was kind of broken through. And so kind of here in the third frame where you see the orange there, that's the liquid mantle coming up from the interior of the moon. It's not that way now, but it used to be. And so when that liquid mantle came up, then it filled those cratered regions and then solidified to give us our mare that we know and love today. The next one, Mercury's cliffs. Actually, I don't have much more to say about that. I've actually heard these cliffs called scarps in other textbooks, but it's kind of like, you know how concrete, you can have a nice, great sidewalk, nice and flat, but then with kind of cooling and heating and cooling and heating, your concrete sidewalk will crack. And to me, that kind of reminds me of the kind of the cracks or the cliffs that we see on Mercury. They're definitely a sign that the interior has cooled to the point of solidifying, which makes sense because Mercury is so darn small. The next one is we've been talking about Venus's thick clouds, and it's very reflective, but we really can't see the surface of Venus. But we know what the surface of Venus looks like, and it's because actually we had spacecraft orbiting the planet, and we could use radar to get a topography, make an image of the surface of Venus. The last one, the origin of Earth's oxygen actually came from photosynthesis of these algae in the oceans. So you figure we had to have a hydrological cycle. We had to have oceans before we could have these blue-green algae form in these oceans, and then actually convert carbon dioxide into oxygen. All right, the next chapter, the Jovian planets. So, let's see, what's the first one? Jupiter. Actually, we talked about how Jupiter and Saturn are kind of like sister planets. Jupiter and Saturn, they both kind of have this kind of orangish sort of kind of color to them. Jupiter definitely has bands, but one of the things your textbook talked about is why we kind of see these different hues in Jupiter. And I know it's hard for you to read this slide, but you can kind of see where it says warmest at the bottom and coolest at the top. So actually, within Jupiter's clouds, we kind of have things, compounds, hydrogen-containing compounds, able to condense under warm conditions and are under then those that need the coolest conditions, and that's where you kind of get a range of colors. The next one's pretty straightforward. What makes our blue planets blue? That would be the presence of methane. The formula for methane is CH4. Those Galilean moons, I went ahead and brought in a figure. So those Galilean moons, it might be helpful to know kind of the order. It's Io, closest to Jupiter is Io, and then Europa, and then Ganymede, and then Callisto. Those are the moons that actually Galileo saw and made note of in his scientific notebook. So the 4 Galilean moons. Let's see. Oh, and then I guess before I move on, actually Europa, and Ganymede and Callisto, but we talked about how Europa has like a crust, an icy crust, and underneath its icy crust, it is most likely liquid water. Let's see, Io. So Io is the innermost Galilean moon, and Io is pretty darn small. And Io is very geologically active. It's definitely got all these little puck marks, and they can actually see materials coming out of those little holes, like kind of like little volcanoes. The materials that come out of Io's little kind of volcanoes is very high in sulfur, so it kind of has this yellow appearance. But Io, the reason it's got this heat going on in its interior actually is from what we call tidal heating. And just like Earth's tides are caused by the Earth's ocean tides are caused by the gravitational pull of the moon and the sun. Similarly, the tidal forces that are causing Io to heat is the planet itself. So basically, I brought in a figure from your textbook down here, kind of in the middle right hand, where they're showing Io orbit Jupiter, and sometimes Io is close to Jupiter, and sometimes it's farther from Jupiter, just like our moon is at perigee and apogee. So when it's close to the planet, then Io kind of has this kind of elongation, okay? And when it's farther from the planet, it kind of relaxes. So it kind of flexes, and it's this flexing actually that causes this what we call tidal heating. The next one. So we looked at an assortment of moons, okay, for that orbit these giant gaseous planets. And we can kind of lump them into large and medium moons, and then on the other hand, small moons. So large and medium moons actually, and we talked about this in the formation of our solar system in Unit 2, those large moons probably formed in like an accretion disk around the planet as the planet was forming at the same time. So they're nice, they have a lot of material associated with them. That makes them spherical, and they orbit obviously the planet in the same direction as the planet spins on its axis. Now the small moons are not large enough to be spherical. The small moons some of them anyway, are most likely captured later. That was my point. Titan, actually I have Titan and Triton here, so I put them both up to confuse you. Titan actually is a large moon that orbits Saturn. And Titan actually has been visited by the spacecraft Huygens. And so in this little inset, I have photographed that middle one there. The last two actually are what the spacecraft sent back when it had landed on this moon that orbits Saturn. Is that not cool or what? Titan is awesome because it has an atmosphere, and actually has a cycle, not of water, but of methane. So actually there's liquid water, not liquid water, there's liquid bodies of liquid ammonia there. I think I've gotten that right. Methane. Final answer. So then the other one, Triton, actually, if you skip a few planets, around the last planet, Neptune is the moon Triton. And so Triton actually orbits, remember, backwards from Neptune's rotation on its axis. So Triton is going backwards. The other thing about Triton is it has this kind of cool cantaloupe surface feature. I don't know. Jovian rings. Actually, all the Jovian planets have rings. Saturn's rings are the coolest, most likely. And so I have a few pictures here about rings. How did the rings form? Well, it's most likely that actually moonlets kind of ran into each other and kind of broke up. Now, rings are generally very reflective, and that's because they contain a lot of ice and such. The rings actually have gaps in them, oftentimes created by the presence of another moon. And the rings themselves actually are not solid. I bet you already got that. They're made of like individual icy rocks. All right, the next chapter, again about asteroids and comets, and I feel like we've definitely kind of carried over Unit 2 now into Unit 3. So they're similar. They're leftovers from the formation of the solar system. In general, though, asteroids don't have an icy component, and comets do. So the asteroid belt, of course, the asteroid belt is located between our last terrestrial and our first Jovian planet. So that's between Mars and Jupiter. And I think this is a homework question. Why is it there? And actually, it's thought that the mass of Jupiter basically gave a gravitational nudge so that we couldn't have something larger than the little crumblies that we have there in the asteroid belt. because it was disrupted by the gravitational influence of Jupiter. Let's see. Trojan asteroids are a type of asteroid that actually escort, the most notable ones actually escort the planet Jupiter around in its orbit, a few in front and a few behind. Those are Trojan asteroids. Actually, Earth has Trojan asteroids as well, but they're not quite as famous. Then there are the M's, the meteoroid, the meteor, and the meteorite. So the way, I don't know how you want to remember this, but I usually think of oids. So meteoroids are kind of like oids or asteroids. So actually meteoroids and asteroids are like the same thing. Meteoroids are just a little bit smaller is how I think of it. A meteor is that kind of light that is created as a space rock falls through Earth's atmosphere. So I put falling here. That's a meteor. And the meteorite is, if there's anything left of the space rock to pick up that lands on Earth, that's a meteorite. Yeah. So meteor showers occur as the Earth is orbiting the Sun, as the Earth pushes through debris that was left by a comet that had passed through. Remember, when we talk about comets actually are being vaporized by the Sun as they approach the Sun, so they leave kind of these crumblies in their wake. And as the Earth passes through what's left over by a comet, then we have what we call a meteor shower. And so there you go. The next one, comet nucleus, comet coma, comet dust tail, and comet plasma tail. So I went ahead and brought in this figure from your textbook, so you can kind of need to know the anatomy of a comet. Now, just keep in mind that most comets, like we talked about in lecture, most comets are out there in the Kuiper belt or the Oort cloud, and they are not fizzing. Most comets are not they're not ionizing, okay? They're just kind of sitting out there minding their own business. But if they get close enough to the Sun, then they can begin vaporizing. I guess that was the word I was after. So let's see. I guess one thing to draw your attention to is in green I have plasma tail, and I say tail is blown away from the Sun by the Sun's solar wind. So it's always blown in the direction away from. The tails it's not like a kite where the tails kind of follow the movement. The tails actually always will be directed away from the Sun. All right, the next one, Kuiper belt and Oort cloud. Of course, those are locations for comets. So these are locations out beyond the orbit of Neptune. And in fact, Kuiper belt actually kind of lies in the plane of the ecliptic. And then the Oort cloud actually is kind of the spherical region, that is more distant than the Kuiper belt, and it lies kind of in a spherical region around the Sun, with the Sun in the center. Then I kind of have an assortment of things: Pluto, Kuiper belt objects, KBOs, Charon, and Eris. So Pluto is actually now considered, as we know, a dwarf planet. And Pluto is much more like a comet than it is like even a terrestrial planet. So Pluto's but Pluto's this beautiful icy object that we are enjoying pictures from New Horizon. But anyway, Pluto began its descent as being a planet by the discovery of an object called Eris. And Eris is another Kuiper belt object, another dwarf planet, larger than even Pluto. So we have a lot of these Kuiper belt objects. Remember, Pluto actually failed. Did I say? No, I didn't say why. But it failed the criteria to have cleared its orbit, and so it failed to be a planet. Charon is I have on that line because Charon actually is the largest moon that I'll say orbits Pluto, but actually they do more of a dance. Okay, so Pluto kind of wobbles and around this common center of mass with Charon. So that's Charon, and I think that about does it. So let's look at the last chapter, Chapter 10. I don't have a lot of questions about Chapter 10, but let's take a look. Chapter 10, we were looking at other stars that have planets orbiting them. And we found out that most stars do have planets in orbit about them. So the term extrasolar planets is what we use to describe planets orbiting other stars. We said, how do you see those planets orbiting other stars? Well, it's not directly. We said actually there are two indirect methods of locating. Oh, let me see. I put something up in green there. Extrasolar planets. Yeah, now I say in green at the upper right-hand corner, I say something about extrasolar planets are hard to detect. No duh, right? Because they're so far away and the planets are so small. And then oftentimes, obviously, the star's light gets in the way of directly seeing the planet. All right, so the two methods of detecting these extrasolar planets, these planets that orbit other stars. There's this one, and it's a gravitational sort of tug going on. And actually, our star and the planet Jupiter kind of do a gravitational tug. So our star is actually kind of wiggling a little bit. So if we see the wiggle of the star, then we know that something's tugging it, and we can actually do the math. Yes, it's all about math. And we can get to information about the planet orbiting that star. The other way in direct detection is actually where we use a light meter, and I would call it the transit or eclipsing method. So basically, we see that the light from a distant star changes as the planet orbits the star. We get all sorts of good information about that. In order to determine the density of anything, basically we need to know a ratio of the mass of the object, in this case the planet, to the volume of the planet. And so with the methods of detecting the planet, extrasolar planet, if we can get a fix on the mass and the radius of the planet, then we can, of course, go from radius to volume, and we can get to the density of the planet. The last one here, why are most of the extrasolar planets that we find, why are they near their host star? And the reason for that, as I understand it, is that you know how like Mercury, it doesn't take too long to go around the sun, and neither does Earth, doesn't take too long to go around the sun. But if you get out to Neptune and Uranus, it takes a long time for them to complete one orbit about the sun. Well, that's kind of the thing we run into with extrasolar planets. So it's much easier to see, to wait and look at an orbit of an inner planet than it is an outer planet, basically because of the time difference.